I'd like to do an example of a calculation in quantum mechanics studying a scattering amplitude, the possibility of an incoming beam scattering off of some barrier. And in this particular case, the story that I've set up is a very simple one, a mathematically simple one. I've got a constant potential energy until I get to x equals 0, and then I've got this just square block-shaped barrier, width a, and height VB, V barrier, and then 0 potential off on the other side. And what I'm going to imagine doing is sending an incoming beam of particles coming in from this side, and I want to know what's going to happen when they come out the other side. If they are going to come out the other side, if they're going to bounce back, what's going to happen? Now, classically, we know how this story generally works. If the total energy of our system is above the energy of the barrier, then I would expect, remember kinetic energy is the difference between your total energy and the potential energy, so I would expect a fast-moving particle coming in, and it would come to the barrier, and if you imagine it's a little bit smooth, it would roll up the barrier and slow down and go slowly across the top, and then it would roll down the other side and go fast out the other side. Classically, any particle with energy higher than the barrier will just come right through and get out the other side. Similarly, classically, if the energy is lower than the height of the barrier, I expect that you'd come in with kinetic energy, you'd come along, and then your particle would go here and it would roll up the barrier until it got to that point, but then it would roll right back down and go back the other way, because classically, a particle without enough energy can't cross over. It doesn't have enough energy to get to the top of the barrier and over to the other side. So those are the classical results. Quantum mechanically, we're going to find the stories a bit more interesting. And to do that, we're going to expect that we're going to have an incident beam coming in, and we're going to expect that, in general, we'll expect some transmitted beam going out the other side, and some reflected beam coming back the way we started. That's our expectation for what this is going to look like. Now, to set this up quantum mechanically, we're going to need to use the Schrodinger equation. I haven't written it down, but I've written down its solutions. We know from basic Schrodinger equation quantum mechanics that if the energy of your particle is less than a constant potential energy, if the total energy is less than the constant potential energy in some region, then the wave function psi of x has to be some linear combination of exponentials, either e to the qx for a growing x, or e to the minus qx for a decaying x as you go to positive x, where q is this particular combination of masses and energies and h-bars and things. Q is based on the difference between the potential energy and the total energy. So this will apply for us if we're having an incoming beam with an energy between 0 and V barrier. This will apply during that intermediate region through the barrier. V naught minus E is just that difference in energy between what we need and what we have to get over the barrier. That's the E less than V barrier region. On the other hand, we know that Schrodinger's equation has different solutions if the energy is greater than the surrounding potential energy. For a constant V naught, for a constant potential energy, we have this constant K that is this time E minus V naught. That applies in, say, this region, where E is greater than V naught, greater than 0. So in this region, we have this thing, this K, that's based on the kinetic energy. E minus V naught is your kinetic energy there. K is directly related to momentum. And there's sinusoidal solutions. Psi of x is a sine of kx plus b cosine of kx, where a and b are complex coefficients in either of these things. It's some linear combination of sines and cosines. That's the usual way I think about it, but remember that there's another way we can write this. Because of Euler's identity for complex exponentials, we can also write this as a linear combination of e to the plus ikx and e to the minus ikx, because e to the ikx is sine of kx, or cosine of kx, plus I sine of kx. It'll just give you contributions. This a and b, of course, are different than that a and b, and different than that a and b. It's just constants. We'll come up with names for our constants wherever we put them. But that's what we come up with. So we have to decide which language to use. Either one is equally good. Either one is equally correct, equally general. But it turns out that we'll find the second one is what we're going to want to use for a scattering problem. For problems of things that are just sitting still, the first one's often easier. But for scattering, the second one is easier. Why is that? It's because e to the ikx looks like a momentum state. We know that our states of constant fixed momentum are basically e to the ikx times some normalization factor. And so that means this will look like a particle with momentum, and that's what an incoming beam looks like. In fact, to be precise, flow, when I say we expected an expected flow of particles to be these incoming, transmitted, and reflected beams, when I say flow, what I'm really talking about is the quantum probability current, J vector, or the x component Jx of the probability current. I'm not going to go into detail about the probability current right now. You can read up on it or somewhere else, or I've got a video on the probability current separately. Roughly speaking, it's just the flow of stuff, the flow of probability of where your particle is in a given situation. And the key idea is it follows momentum really closely. So if you have a momentum state, that will correspond to a state with definite flow. We want that. That's what's going to be the natural language to describe our situation. So we're going to use this form for our wave function. Now, when I say our wave function, remember we've got three regions here, and the way that we solve Schrödinger's equation when we have regions with different potential energy functions is we're just going to define separate wave functions in those regions. So I'll have a psi left of x that's going to apply anywhere left of x equals 0. I'll have a, psi middle of x that will apply anywhere between 0 and a, and I'll have a psi right of x that will apply anywhere for x greater than a. And our goal is going to be to use boundary conditions, the behavior at infinity and behavior matching up these boundaries, to figure out what the coefficients will be to mix these different functions that will make this work, that will give us some fixed idea. So we're going to take E as given, the energy E as given. We're just going to assume we're choosing some energy to send our particles in with, and our question will be, how likely is it those particles will be transmitted? How likely is it they'll reflect back? That's our idea here. So what are my functions? Well, psi left of x is going to be exactly this, the exponentials here. I'll call it a e to the I kx plus b e to the minus I kx. That's my psi left function. Psi middle of x is going to be, I'm going to hold on. This one, maybe I've done this in a bad order. Psi middle, let me give coefficients in a second. Psi right of x is going to be another one in this form, so I'll call this c e to the I kx plus d e to the minus I kx. Got those pieces. And psi middle is the one that's going to be up here. I'm not going to use e as a coefficient because I've already got e for energy. So I'm going to use f and g. I'll say that this is f e to the qx plus g e to the minus qx. And again, k and q are defined over here in this in our basic definitions. So these are the three functions I'm going to use. And in general, this has to be true. This is what we have. This is how you set up an equation like this. How you set up a Schrödinger's equation solution in quantum mechanics. You just find the regions. In each region, you say, what's the potential like there? What kind of function solves it? And then you write these down. This is very general. And so we have to limit ourselves a little bit. We look at this, and we want to, oh heavens, I'm going to ignore my phone over there. Sorry about that. We're going to go ahead and we're going to solve our psi of x functions that will go through and find those find those boundary conditions. So here's what we need to do. I'm going to point out that the probability current, the probability current Jx for the left region, if I were to work out that, you can look at my video for probability current and see what happens here. If you work that out, that's going to be, if I write it down precisely, it's going to be h bar k over m times a squared minus b squared. And the probability current, Jx, for the right region is going to be h bar k over m c squared minus d squared. And what this means is it's just telling you something about how current is flowing through this situation, how particles are flowing through this situation. And what it tells me is that this A, the A coefficient here corresponds to a positive flow of probability. That's a rightward plus x flow. So this I'm going to identify as my incident beam. B corresponds to leftward flow of probability. So I'm going to identify it as my reflected beam. corresponds to rightward flow of probability. So I'm going to identify it, since it's in this region, as my transmitted beam. And D, what's D? D would be leftward flow of probability in this region. That would be an incoming beam from the right. We don't have that in our setup. We've assumed our incoming beam is only from the left. So we don't have a D. So that tells me that my coefficient D has to be 0, or else we would have an incoming beam from the right. Already I've limited my questions a little bit, limited things a little bit. So at this point, I've got this, I know what my coefficients have to be to get my incoming, my incident and reflected beams. I've got an idea about what that flow of probability is going to be. Now, we've used this is basically boundary conditions at infinity, knowing I have that set of beams and not that one. We've applied our boundaries at infinity. So now is where I impose the conditions that our wave function has to be continuous and smooth. So wave function conditions, let me just, I need the psi of x to be continuous at all points. And so in particular, the places I'm worried about this are at the boundaries, x equals 0, x equals a. That's where I'm worried. So at x equals 0, continuity requires that these two functions have the same value at x equals 0. That tells me psi left of 0 has to equal psi middle of 0. And, well, I can just plug in x equals 0 to these two equations. I'll get that a plus b equals f plus g, because that's just, e to the 0 is 1, so that's just my x equals 0 condition. And at x equals a, I need psi middle of a equals psi right of a. And so this will be a little bit more interesting. I want to set these two equal at x equals a. That tells me that f e to the qa plus g e to the minus qa has to equal, and then psi right, c e to the ika. There we go. That's my condition for continuity for psi of x at those two positions. I can then go on and I can say I also need this wave function to be smooth. Psi prime of x has to be continuous. This condition is true any time that your potential energy is not infinity. If you have a potential energy, that like a particle in a box where you have an infinite potential energy somewhere, you don't need to have this smoothness criterion, the derivative being continuous. If you have a delta function potential, where you have an infinite spike or infinite dip or something, you don't need the derivative to be continuous. At those points, you can have a wave function with a sharp edge somewhere. But otherwise, it needs to be a smooth function. And so I'm going to do the same thing. I need the derivatives to be continuous. So at x equals 0, I need psi prime left of 0 equals psi middle prime of 0. Those derivatives of exponentials, fortunately, are really easy. I just pulled out an ik. And so this one tells me that ika times e to the 0 minus ikb times e to the 0 equals qf times e to the 0 minus qg times e to the 0. So I've got that equation at x equals 0. And then at x equals a, I've got the same idea. Psi middle prime of a equals psi right prime of a. And there, again, I get an uglier equation. I get the same sort of thing. I get here qf e to the qa minus qg e to the minus qa equals, and then for this one, ikc e to the ika. There we go. I've got another equation. And let me look at this. Let me label my equations. I've got 1, 2, 3, 4 equations. 4 equations. And let me think about my number of unknowns right now. We have 4 equations. 4 independent equations. What are my unknowns? I'm taking E to be given. My energy is a given quantity for this problem we're solving. And I'm taking my A. I can take A to be just a measure of the strength of the incoming beam, the intensity and amplitude and phase of the incoming beam. So I can say that E and A are given values, because I could tune A to be anything I wanted. Send more particles, just make A bigger. E and A given, so my unknowns are going to be B, C, F, and G. So I've got 4 unknowns. 4 equations and 4 unknowns. Any physicist will tell you, mathematicians will wince, but any physicist will tell you there's a unique solution, or at least we don't have some unbounded number of solutions. We don't have an inconsistent system. 4 equations and 4 unknowns, we can find this answer. It's ugly. You can do this. You can do this, but it comes out to be an ugly answer. Let me just tell you what I come up with when I've gone through this. Look, lots of ugly math. When I go through this, the answer I end up getting, the interesting parts of my answer, end up being that the coefficient C, remember C is the coefficient of the outgoing beam, the transmitted beam. The coefficient C that I come up with looks like ugly fraction. It is 4IKQ e to the minus IKA, little a is the width, remember, times our coefficient A, all divided by, and again, I told you this is ugly. As simple as I could make it look, Q plus IK squared e to the minus QA minus Q minus IK squared e to the plus QA. That's my Q, that's my C coefficient. But you can see I've got an answer in terms of A was given, K and Q are given in terms of the energy and the V naught and the other given things in the problem. And this is all in terms of those given quantities. I've got a result for C. I could, if you want to rearrange this, you can play with this at home, kids. If you want to rearrange this, we could write this as 2IKQ e to the minus IKA times A divided by, this form is a little bit easier to do absolute squares with, K squared minus Q squared times the sinh, the hyperbolic sine of QA, plus 2IKQ times the cosh, hyperbolic cosine of QA. Sinh and cosh are just e to the plus QA and minus e to the minus QA, or e to the plus QA plus e to the minus QA, divided by 2 in either case. So this is just rearranging this thing. What that means is that the absolute square of C, if I do the absolute square of C, you get their sinh and coshes in the most natural way of expressing it. The result I wind up getting for that absolute square winds up being this ridiculous thing. 1 over 1 plus K squared plus Q squared over 2KQ squared times the sinh squared of QA. And that's all in the denominator, this 1 over thing. That's my transmission, that's my C squared. Oh, I forgot one more thing. Absolute value of A squared. I need to have that, the absolute square of A is my numerator. That's my transmission coefficient essentially. That's how much transmitted beam that I have coming through. And we define, in a scattering problem, once I have this, we define the transmission coefficient T is defined to be Jx for the transmitted beam divided by Jx for the incident beam. So it's just, this is the probability current. The probability current for the transmitted beam is this. Probability current for the incident beam is this. So this, in our case, ends up just being C squared over A squared, absolute squares, which is just this thing with that a taken out of the numerator. It's just 1 over this thing is my transmission coefficient. And there's not a whole lot of intuition you get from this, I guess. It's kind of a messy thing. The one thing I'll point out is that as your QA goes to infinity, so as the barrier becomes wider and wider compared to the Q is sort of the exponential decay factor, as the barrier becomes wider and wider for fixed energy, we'll find that T approaches, this thing, sinch becomes e to the minus QA as the QA becomes big, and so sinch squared is e to the minus 2 QA, and then this thing is down here. This term gets much bigger than 1, so I end up getting that this is 2kq over k squared plus q squared times e to the minus 2 QA in that limit, that T becomes this exponential decay of the width, basically, exponential decay factor of the width of the thing. And this is squared, sorry, this is squared. It turns out that that squared term actually can be written in a pretty elegant way. It turns out this is equal to the energy divided by V naught, E over V naught, times 1 minus E over V naught times e to the minus 2 QA. So that's this KQ factor squared turns out to be this ratio thing in terms of ratio of the energy to the V naught. What fraction of the total energy, total potential barrier do we have as our energy? That's what this comes out to. So as your energy gets bigger, well, these terms, you can see there's some optimum in the middle where this term becomes optimal if E is halfway up. But of course, the closer E is to V barrier, I should have said V barrier, shouldn't I? V barrier, yes. V barrier, V barrier. The closer the energy is to our barrier energy, the e to the minus 2 QA falls off slower and slower because Q becomes a bigger and bigger exponential. This is how you solve a scattering problem. The key ingredients, now I didn't show you all the math here, but the key ingredients, the part you need to do to solve a scattering problem is you break up your system into regions, different regions with known wave functions in each one, whatever they are, write down those wave functions. You interpret the incident beam as the one with e to the ikx on the left, in this case. You figure out which part is your incident beam, which part's your reflected beam, which parts are transmitted, which parts shouldn't be there if you only have one incident beam. So you put those conditions in. Just think about it. This is always the form that this probability current takes. And then you just apply the conditions that the wave function has to be continuous at the two boundaries, or however many boundaries you have. You want it to be continuous, and you want it to be smooth, its derivative being continuous at the two boundaries. That gives you two conditions per boundary, and that'll come out to be the right number of conditions to solve for all your unknowns, all your coefficients, in terms of the given stuff, the energy and the incoming intensity and phase A. That's what we got. That's how you do a scattering problem, and I hope this has helped clarify the ideas a little bit.